Now that we have our new combination theorem of the generic case of two mirror planes, I want to go back and rederive the way that we'll use it now. Like, suppose that we didn't do it by inspection for the 2mm group. I remember when we did the 2mm by inspection and said, oh, there's an extra mirror plane sigma 2 here, and this led us to, all right, let's think about this as a group, and we showed that two operators, operating on each other give a third member of a group. This is probably a part of a group, and it's a complete point group. And that led us into looking at that representation. We went off on a little bit of a deviation talking about point groups and subgroups. But now that we've derived the generic expression in the last class, let's go back just to be consistent with the way we're going to use it now, and let's look at 2mm as a specific case for the general theorem. So the generic theorem was, I'll write it here, remember that if we had an angle mu between sigma 1 and sigma 2, sigma 1 and sigma 2 operating on sigma 1, then you would end up with a rotation equivalent of 2 mu. And you can see over here that we've done is, all right, fine. This is how we're going to use the theorem if the angle that we're going to rotate about at the end of the day is a 180-degree rotation, then the planes are going to be pi over 2 apart. So in other words, if I use this now, the way I would do it, knowing that I have this generic expression now, what I've done is said, all right, I have a twofold symmetry axis, which remember is essentially a pi, right? So I know that I'm going to be using a pi, so mu equals pi over 2, and therefore if I take this theorem and I put a sigma 1, through an a pi, if I look at this theorem, it says, aha, that means that 90 degrees away from sigma 1, I have to have a sigma 2. So 90 degrees away, I have to have sigma 2. And because it's a unique element formed by the operation of 2 on each other, that results in the fact it's unique. And so again, when I go to write the point group, 2 is for the twofold, m is for sigma 1, and then the second m is for the sigma 2. And that goes to show you how we did the specific case before. Now with the generic case, you can see how we can use this. And now in the next lecture, let's go on and show how we're going to use this for the four-fold axis combined with a mirror plane, and what kind of point group that creates.